Okay, this next part of linear algebra is about linear systems. And, we talked a little bit about linear systems earlier on in the refresh. You recall that we had a system of equations where you have n variables, n equations, and then you can solve for the variables. Linear algebra helps to make this simpler because you can take a problem that has a number of different equations, a number of different variables, but you can state it in a very compact way. Instead of having all the equations written out, we could say that we've got matrix A. And so we've got 3, 9, 4, 8. And then we've got down here, let's say we've got a vector y. So we've got 5 and 12. This is the one we were doing earlier. Basically, we can say that we've got a system of equations like a times y equals, a times x equals y. Okay. So if we know that we've got our y's defined, we've got our a defined, our coefficients, we've got the system of equations we're trying to solve for x, we can think of it in terms of just having this very simple statement of an equation, a times x equals y, x being a vector and y being a vector. And so we've got two unknowns, two equations, solve for x. Now, one of the things that would be nice to do here would be to say, well, what if we could just take and divide by a from both sides? So ostensibly, if this was just a simple problem in algebra, you could say a times x divided by a would be y divided by a. You divide both sides by a. And that would be nice if you could divide by a matrix, but that's kind of problematic. So can't really do that. However, what we can do is define the inverse of a matrix. And so rather than dividing, we multiply both sides by its inverse. So we could say a times -1 as the inverse times ax equals a -1 times y. And in that case, then this side drops out. You end up with x equals a inverse -1 times y. So rather than dividing, you can just multiply by the inverse. And we have this notion of a matrix inverse. We can also state something like a times a to the -1. A matrix times its inverse is going to be equal to identity matrix. So the identity comes back in pretty handy here. Finding an inverse of a matrix can be tricky business. We have to take and rearrange the elements and divide by the determinant. This is a point where the determinant comes in really handy. And it's only going to work on square matrices. But if you want to do it, if you want to calculate it in Python, NumPy makes this very simple to do. OK, I've got some Python based on NumPy, and I'm going to take and define my matrix A and my vector y. And let's see here. First, I'll cut and paste those. So I've got A and y. OK, now I'm going to define another variable, inverse A. So again, using the linear algebra package out of NumPy, I've got A. OK, I've found what the inverse of matrix A is. It's this other array, 2 by 2 array. OK, and now to show something interesting, let's try this. Let's multiply an inverse of a matrix times the matrix itself. Should come out with the identity matrix. 1's in the diagonal, 0's everywhere else. And now let's take and solve for the problem we have down here. We can solve this equation, ax equals y, by multiplying both sides by the inverse of a. We come out with x equals the inverse of a times y. OK, great. We get that solution, 5.67 and -1.3. OK, so here's a big idea. We had solved for n variables and n equations. Now, what happens if those don't match up? What if you have more variables than you have equations? Or what if you have less variables than you have equations? So we have two notions here we want to introduce. One is something called overdetermined systems. Suppose that you have more than n equations, then really there could have been too much data, and there's no exact solution possible. In those cases, what we usually do is something called approximation. We approximate an answer. Now, on the other hand, suppose that we had less than n equations. This is something called an underdetermined system. Essentially, there would have been too little data and consequently too many possible solutions to fit that. In those cases, we want to optimize. So a general way to look at it, if you've got n variables, if you've got less than n equations, you're going to be doing optimization because you've got an underdetermined system. And so an example of that, which we'll get to in a bit, is linear programming. If you've got more than n equations, that's going to be an overdetermined system. Then you're going to typically do some kind of approximation. Least squares approximation, curve fitting, that's an example of that. So this is a handy chart. This is a way of thinking of things that you want to compare how many variables versus equations you have. Now, in terms of computational thinking, let's try to generalize from this pattern. And an abstraction here is that the relation of the count of equations and variables helps us decide which kind of approach we want to use. In some cases, we may want to add a synthetic variable, or we may, in some other cases, may want to fix particular variables temporarily so that we can shift between optimizing, solving, and approximating. We may want to shift back and forth depending on the kind of problem. But thinking at this level of abstraction, you can figure out which to use. Now, in terms of linear systems, I was showing a 2x2 matrix there. It's a relatively small example, about as small as you can get. These kinds of linear systems in practice tend to grow very, very large. Finding a matrix inverse in the case of having a really huge, enormous matrix, that may be expensive, it may be problematic in other ways, it may not be numerically stable in certain ways, especially for certain kinds of approximations. So, we struggle to find ways of performing the math without calculating a matrix inverse. And we'll get to some of those examples in a bit. But again, a matrix inverse may not always be what you want to use.